We are going to talk about the algebraic equations with an unknown. That is, we are going to see what an algebraic equation is. We are going to solve this type of equations with a single unknown. And we will explain what is the rule of Ruffini to solve them. For this reason, just knowing the operations with real numbers is enough. So, we will start by defining what an algebraic equation is, with a degree n and an unknown x. It is an equality of this form, that is, where we have a sub n by x raised to n plus a sub n minus 1 by x raised to n minus 1, etc., up to b, with some a sub I different from 0, so that we have an equation. If the a sub I that is different from 0 is the n, then the equation has a degree n. Obviously, all these a sub 1 and a sub 2 to a sub n, which we call coefficients of the equation, are known real numbers, and b is also a known real number that we will call independent term. The only thing we don't know here is the unknown x. So, for example, we have many types of equations. 2x minus 5 equals 0. It would be an algebraic equation of degree 1. 3x squared minus 7x equals 9. It would be an algebraic equation of degree 2. The degree is marked by the highest power of the x. This last one would be an equation of degree 4, and that is how we could build all the equations we wanted. We are going to talk about solving the equation, so we have to know what a solution is. It is considered the solution of the algebraic equation any number that meets exactly the equation. That is to say that when we substitute it in the equation, it is satisfied identically. Solving an equation will be finding all the solutions of it, or determining that it has none if it is an equation without a solution. So, for example, for the equation 2x minus 7 equals 0, we can prove that 7 halves is a solution, since if I substitute the x by 7 halves, this is an identity. The equation is directly satisfied. That is what to be solution means. This equation has a single solution. This other, x squared plus x minus 2 equals 0. It would have two possible solutions, the 1 and the minus 2. In fact, substituting 1 in the x, we see that it is completed identically, and substituting minus 2 in the x is exactly the same, then both are solutions. And so, for this other equation, we would have 4 solutions. The number of solutions will depend on the degree of the equation. This other equation, x plus 5 equals x, does not have a solution, since it is impossible to find any value of x that satisfies this equation directly. Then we will say that this equation does not have a solution. How are we going to solve the equations? Well, depending on the degree of the equation, we have to do one thing or another. If the equation has a degree of 1, then by directly solving the x, we have the solution. X is equal to minus b divided by a. And it is done directly in any example. For example, in this case, x is equal to minus 7/3. In this case, the equation of degree 1 is simple to solve. When the equation is degree 2, x squared plus bx plus t equals 0, they have this expression with a difference from 0, so that it is degree 2. Then, the solutions are given by this expression. Minus b plus minus b squared minus 4a, c divided by 2a, where a and c are the coefficients of the equation. Thus, they give us the two solutions. For the plus sign, it would have a solution. For the minus sign, it would have the other one. And the type of solution that it has depends on how the b squared minus 4ac is, which is what is inside the square root. So, for example, if b squared minus 4ac is positive, then obviously two real solutions are obtained, since the square root of a positive number is a real number. We would obtain the solution with the plus sign, minus b plus b squared minus 4a, c divided by 2a, and the root with the minus sign. And also, this would imply that the polynomial ax squared plus bx plus c can be described as a times x minus alpha 1 times x minus alpha 2. Therefore, obviously, if this is equal to 0, then alpha 1 is a solution and alpha 2 is another solution. What happens if b squared minus 4ac is equal to 0? In that case, this root here disappears since it is 0, and with which I obtain a single solution, minus b divided by 2a. So, this is the only solution of the equation, and then the polynomial x squared plus bx plus c would be described as a times x minus alpha squared. We would say that it is a root of multiplicity too, since it would appear twice as a solution. And if b squared minus 4ac is negative, then the root of a negative number only exists if we work in the complex number body. Therefore, it would be a complex number. For the positive root, we would have the root of minus b squared plus 4ac. That is, we would change the sign because we add the imaginary number I. Then we would have minus b plus root of b squared minus b squared plus 4ac times I divided by 2a. And the other root would be with the negative sign. As you can see, they are complex numbers conjugated. That would imply that the x squared plus bx plus c could be described as a times x minus alpha 1 times x minus alpha 2 with alpha 1 and alpha 2 complex numbers. Or, if we want to get rid of some of the complex numbers, another way to decompose it is as a times x minus p to the square, where p is the real part of any of the two roots, since it is the same, plus q to the square, which is the imaginary part of any of the roots. It does not matter the sign, as the square will give the same result. This is another way to decompose the polynomial and find the roots of this algebraic equation of grade 2. For example, in this case, the equation x squared plus x minus 6 equals 0. By applying the formula that we have seen, it turns out that it has two roots, the 2 and the minus 3. Two real roots, since b squared minus 4ac is 25. That is to say, it is positive. Therefore, x squared plus x minus 6 can be described as x minus 2 times x plus 3, the two roots that have been found. In this other case, 4x squared minus 4x plus 1 equals 0. When I apply the formula, I get x equal to 4 plus minus the root of 16 minus 16, which is 0, divided by 2a. This is 8, and this gives 1/2. That means that this polynomial is described as 4 times x minus 1/2 squared. And in an example of complex solutions, it would be x squared minus 6x plus 13 equals 0. That, as you see, b squared minus 4ac, 36 minus 52, is negative. Therefore, it happens to be imaginary numbers. In this case, the roots are 3 plus 2i and 3 minus 2i conjugated complexes, and it allows to write x squared minus 6x plus 13 as x minus 3 squared plus 2 squared. Well, if we continue solving for higher grades, we have, for example, the biquadratic equations, which are those in which the odd grades do not appear, x to the fourth plus bx squared plus c equals 0. As you see, x to the cube and x does not appear, and in this case, we can make the change z equal to x squared, so the equation becomes a quadratic equation. Then we can apply the formula that we have seen previously, and then it would be enough for these solutions that we find to apply the root again to obtain the solutions of the original problem, of the original equation. For example, x to the fourth minus 13x squared plus 36 equals 0. So if we apply the change, I have z squared minus 13z plus 36 equals 0. Applying the formula, I obtain 9 and 4. Therefore, the solutions of the starting equation would be x equal to the root of 9 and x equal to the root of 4. So the solutions are plus 3, minus 3, plus 2, and minus 2. The four solutions of this biquadratic equation. Well, when the equations are not biquadratic and we have more degrees, then what can we do? Well, we have the equations of degree higher than 2, in this case, to solve this type of equations in general. If they are not biquadratic, then we would have to apply what we know as the Ruffini rule. The Ruffini rule allows us to check if a real alpha number is a solution or not of the equation, as in the following way. I put the coefficients a sub n minus 1, a sub n minus 2 in a row, a sub 1, a sub 0, and I'm going to test if alpha is root. So the first one, the a sub n, goes down directly to this side here. The next operation, well, we are going to see it with an example, since it is much easier to see how it works with numbers. Then, for example, if we apply it to this polynomial, x cubed plus 3x squared minus 4x minus 2 equals 0, then the coefficient of x cubed, the coefficient of x squared, the coefficient of x, and the coefficient of independent term with its sign. So we are going to check if 3 is root or not. As we have said, one goes down directly, the first one goes down directly. What do we do next? Well, we multiply this as sub n by alpha, and we put it here. And now we add it to a sub n minus 1 plus a sub n times alpha. With numbers, we can see that, well, 1 times 3 is 3, and 3 plus 3 is 6. What do we do now? Well, this number that we have here, we multiply it by alpha, and we put it here. If we call it bn minus 2 to simplify the notation, well, bn minus 2 times alpha, I put it here and I add it again. And I add it, it gives me another number. In this case, it is 6 times 3 is 18, and 18 minus 4 gives me 14, and so on. Now, this number is multiplied by alpha. I put it here and I add it until it reaches the end. That is, until it reaches the last a sub 0. In this case, for example, 14 times 3 would give me 42 minus 12 gives me 30. Well, that r is going to determine if the number that we have put here, this alpha, is a solution or not. In fact, if r is different from 0, then we can say that the alpha number is not a solution of the equation. In the example that we have seen, alpha equal to 3 is not a solution of the equation since r has a value equal to 30. And if r is equal to 0, then we can say that alpha is a solution of the equation, and also that the polynomial can be described as x minus alpha, the solution we have found, times bn minus 1 times x raised to n minus 1, bn minus 2 times x raised to n minus 2, and so on, plus b1 times x plus b0. We have decreased a degree the polynomial that multiplies x minus alpha. In the example that we were seeing, remember it was this equation. We have seen that alpha equal to 3 is not a solution of the equation. Let's check the value of alpha equal to 2 so that you can see how it would be done. Look, 1 would go down directly. 1 times 2 is 2. It would add up, so on, with all the others. And the remainder, in this case, is 0. That implies that x equal to 2 is a solution and allows me to write the polynomial as x minus 2 by x squared plus 5x plus 6. Then, if I want to continue finding roots of this polynomial, I only have to solve this quadratic equation since x equal to 2 has already been found. I solve the quadratic equation and obtain that the solutions are minus 2 and minus 3, apart from the 2 that I have found before. That is, the polynomial is written as x minus 2 times x plus 2 times x plus 3. And I already have the 3 solutions of this equation. Let's see one additional example of grade 4, for example, but in this case it is not biquadratic since we have the term in x. I have put it so that you can see that you have to place all the coefficients, even those that do not appear. X to the 4th has a 1, x to the cube is not there, then it has a 0 there, x squared has a 2, x has an 8 and the 5. And let's try with the minus 1 to see if it is root. We use it and get that by applying the Ruffini's rule. The remainder goes to 0, the r goes to 0, thus we can say that alpha minus 1 is a solution, and therefore this polynomial is written as x plus 1 times x to the cube minus x squared plus 3x plus 5. Now we would have to calculate the roots of this grade 3 polynomial to continue finding roots of the grade 4 polynomial. We can try again with the minus 1 because it can be a double root. If we try again with the minus 1, we see that it turns to be a root again, so it would be x plus 1 times x plus 1, because it is a double root, and now what it is left is x squared minus 2x plus 5, a polynomial, a quadratic equation that equals 0. Applying the formula that we have seen previously, and we get 2 complex roots, 1 plus 2i and 1 minus 2i. Then the solutions of the equation are minus 1, which has been found twice, 1 plus 2i and 1 minus 2i, which implies that the polynomial is x plus 1 squared times x minus 1 squared plus 4. Well, with this we have seen what an algebraic equation is, how it is solved, and how the Ruffini rule is applied to solve this type of equation.